So the video you're about to watch is a tutorial recorded live, a live coding session of how to use the basics of PyCA, which is a library to implement cellular automaton in Python. If you prefer written instructions, you should check out the written tutorial in the description, which essentially cover the same topics as the video. And otherwise, enjoy the video. It's a very, live video. I stutter, I make mistakes, but I think it's the best way to learn how to use the library is to really saw somebody do it live, and encourage you to try and do it, follow the steps on your own computer as you're watching the video. Enjoy. Okay, welcome to this tutorial that will be about using PyCA. So first of all, what is PyCA? So PyCA is a Python library that is designed to make it very simple to play around with artificial life models in an interactive way. So it makes it simple to implement your own cellular automaton, let's say, and it makes it also very simple to add some interactivity so you can play with it in real time. So the goal of today's tutorials is to look at the very basics of PyCA. So the plan is that we'll first see how to install PyCA very roughly. If you want more information, you can follow the README, and I'll also add in the description some notebook that essentially is a tutorial for how to use PyCA. Very similar to this video, but as a written tutorial. So we'll start by saying a little bit how to install PyCA, and then we'll go through how to use PyCA out of the box without any coding. So just how to use the pre-implemented models and how to play with them. After that, we're going to implement our own simple cellular automaton. So we're going to implement Game of Life to see how we can use PyCA to implement our own. And then we'll finish by adding some interactivity with the keyboard, mouse, and also with interactive elements in the user interface. So let's get started. So I will assume that you already have cloned the Git repository or downloaded it. So here it is, opened in VS Code. And so the first thing you're going to want to do is just write uvsync and run that command. So if you don't have UV, you can take a look at the README. It guides you through how to install it. And basically this setup is also detailed in the README. So now, since I am on Windows, the README tells me to copy paste this extra command. If you're not on Windows, or if you don't have a graphics card, you don't need to do that. But since my computer has an NVIDIA graphics card, I will also add this command. So as you can see, it's installing some packages. So let's wait for them. Great. So now PyCA should be installed. And the first thing that you can try is to run this command here without the D. If you just have a CPU, if you don't have NVIDIA GPU, you can just run this command. So let's just try it. First time it starts up, it takes a bit of time to start up, but let's see. And hopefully this should open the basic PyCA window. So let's see. All right. It has opened it, and it is extremely laggy because it's using a CPU. But as you can see, this is the PyCA window, and I will explain briefly how it works. But before that, let me show how you can run it if you have an NVIDIA GPU. You can just add the parameter -d CUDA to tell it to use the device CUDA, so it means the GPU. And now it's much more fast. So you can still use it with a CPU, especially if you're on Mac. It works reasonably well, but some of the automata will run not as well. So if you're on a CPU specifically, you can tell PyCA to start at a lower resolution. So let's say 100 by 100 with the parameter W here. So if you go on simulate.py, you can see all the parameters here. And I will also add it to the README. Okay, so here we can see that it's much more zoomed in and it runs more smoothly if you have a CPU. So that's basically it for installing PyCA. It's very simple. Just copy the repo and run this UV command. So now let's go about understanding a little bit the interface, right? So let's take a look at the interface. I will run it with a GPU because it's a bit smoother. And we'll take a look at the basic interface. This might slightly change over the years as it gets a bit better and more beautiful, but it will mostly be the same. So let me put it in full screen. So on the left here, you have some information about the currently selected automaton. So we can see it's called Lenya. Here you have a small description about the automaton. And below you have keyboard shortcuts. So these are the general controls that you can use. I will not describe all the shortcuts, but for example, let's see. Here, by pressing C, we can reset the camera position and zoom, right? So here we reset the position. Or we can see here that Control plus drag will move the camera, or Control plus wheel will zoom in and out. So this is very handy to refer to if you want to do different things. So as you can see, for example, space is to start and stop the simulation. So I can start the simulation. And I'll let you explore a little bit this, but you can also record the simulation. So let me go to, let's say, the cellular automaton here. This is Game of Life. So you see it's a R toggle recording of the simulation. If I press R, you can see this little red dot. When you press R again, a video will be saved, and we'll see where. I'm not going to go into depth of the UI, just give you a feeling for it, and then you can explore on your own. So these are the general controls that are the same for any cellular automaton you would run. And then here you have some specific controls about the specific automaton that you run. So here, for example, we see that by pressing delete, we can reinitialize the automaton. As you can see, if I press delete, it reinitializes. They say, for example, press up for longer lasting highlights. So I can press up. And as you can see, the highlights last much longer. And I can press down repeatedly to basically remove the highlights. Okay, just as a last example, I can press del again to restart it. And I can pick a new random highlight color with Z. So you see it becomes red. And so if I go to another automaton, let's say this one, you can see that here the automaton keybinds have completely changed. So I have a bunch of different keybinds. So you should always refer to this part here if you want to see what you can do with the automaton. And here in particular with this automaton, you also have mouse control, so you can remove and add matter with the mouse, which is not written here. It should, that's my bad. Anyway, the last thing on the left here that you're interested in is this green string. So this, depending on the automaton, will give more or less information, but it's basically some live information about the automaton. For this one, it's very cryptic. It's not very clear what's happening, but let's see. If we go into Lenya, yeah, no, not much better. This one doesn't have anything here. So yeah, as you will see, yeah, for CA2D, it tells us the rule is S23 and B3. So as you will see, a lot of the automata, they all work well and they all have some level of interactivity, but they are very much not complete and polished. Okay, so this will probably evolve across time, and the automata will be better documented and more polished. But for now, yeah, it's already very good enough to test all these automata. So now let's go on the left. So here, as you can see, we have an FPS counter that tells us the frames per second. And here we have a box which determines the target FPS. So here I want it to go like 30 frames per second. You see it's slowed down. Here I go to 60 frames per second. So for now, the one step of simulation of the automaton corresponds to 1 frame of the video. That's pretty bad, especially with Pygame. So in the future, this will be different, and you'll be able to choose how many simulation steps per second you want and how many frames per second you want, which is usually 60 or 100. Here, these should have labels, so they will have probably in the versions that you will see. This allows you to change the size of the world. So let's here make a 50 by 50 world, or I can make a much bigger world. Don't do this if you're on CPU because you'll have problems, right? So now the world is much bigger. so that you can control the automaton world. Of course, as you can see, you can resize the window, the PyCA window, which is independent of the size of the automaton. Let's go back to full screen. And finally, here on the left, for some of the automata, this is still in progress of being implemented, there are some buttons that you can use in addition to the automaton keybinds. So for example, here I have a reset button, which will reset. So this does the same as pressing delete. I can change the initialization from noise to dot. Of course, in this automaton, the dot doesn't do much. But if we change the random rule, like if I click random rule, so this is another automaton rule. Oh, that's not a nice one. Most are not nice. So there it is. Now the initialization with a dot is very different than the initialization with noise, right? Okay. And then here we have the new color. And finally, below here on this button is the automaton selection. So these are all the cellular automata or artificial life models that are already implemented. So let's see, for example, falling sand. Yeah, this is pretty slow because it does not use the GPU. So I'm going to make it a bit smaller. Let's go 100 by 100. So here we have a nice falling sand simulation. And we see that with left click, we can add material. With right click, we can remove material. We can adjust brush size. And we can toggle sand and water. Okay. So this is the most fun part. So I encourage you to go and explore all the cellular automata that are available in this list. Some might have some bugs, but most are very cool to explore. Some are not very well documented. Some are harder to use, but it's still fun. So that's basically it. So this is the PyCA interface. And what PyCA allows you to do is makes it very simple to implement an extra automaton to add to this list, and also makes it very simple to kind of add interactivity as we have seen here. So the next step is to now go on and get our hands dirty and implement our own game of life as an example of how to implement stuff in PyCA. Okay, so let's get started. Okay, so let's start by taking a look at the PyCA Codebase, because if we are going to dive into the code, we need to be able to kind of run around it a little bit. So most stuff is contained into this PyCA folder, okay? You have some extra folders like demo data, which contains some data for the automata that you saw that is saved. You have some extras, which at the moment is just training some neural cellular automata code. And the rest is the simulate script that we just use to run the simulation. And so everything will happen inside PyCA here. So let me give you a very basic understanding of how PyCA works. Basically, all the models that you saw, all these simulations that you saw, they are subclasses of this main class called automaton. So every time that you want to create your own model, you will be creating a class that is a child that inherits from automaton. And as you can see from the description, it is a class that internalizes the rules and evolution of an alive model and subclass it and define self.step and self.draw at a minimum to have a model that can run in PyCA. So all you need to do to create a new automaton in this list that we saw at the beginning is to create a class that inherits from automaton and then define self.step and self.draw. So where do all these models live? Where it's inside automata and then models. So here you can see that you should recognize the name that we had in the list. We have, for example, reaction diffusion here. As you can see, it inherits from automaton. We have CA2D, which is 2D cellular automaton, also inherits from automaton as it should. And you have the more complex classes here inside the linear folder. So the first step, if you want to create a new cellular automaton, is to go inside models, create a new file, and let's create our model, which we'll call newGol.py. Right? Then you want to import the automaton class, like so. Sorry. Okay, and then start by defining your new automaton class, re-implement a live re-implementation of Go. By the way, I'm doing this tutorial without any of the AI autocompletion or AI agents. It's been a while since I've coded without these extra tools, so it will be a bit slower, but I think it's better in terms of pedagogical value. But of course, it goes without saying that if you put Claude Code on this code base and ask it to implement an automaton that you specify, it will be able to do it without any problems. But okay, let's do it ourselves still to see how it works. So first define an init function. And for the init function, you can put whatever you want, but you need to at least include the size and a device. So size is a simple tuple that contains the height and the width of our cellular automaton world. That's it. The device is because this whole code base, I haven't said it, but it's very intertwined with PyTorch. Right? PyTorch is, if you don't know, is a machine learning library primarily, but it allows you to do computations on the GPU very easily, and it allows you to parallelize computations. And since cellular automata and in general artificial life model are very easy to parallelize, it's very useful to use Torch. So for now, Torch is an essential piece of this library. And so that's why every cellular automaton has a device, which will tell Torch whether to be on CPU, on GPU, or some other acceleration engine like MPS on Mac. You don't have to use Torch, to be clear, in your implementation of the automaton, but for the purposes of this tutorial, we will, because it's just simpler for me, and in general, it makes things simpler when you want to do things efficiently. But you don't have to in principle. So our init function for our automaton need to have at least a size and a device. So for now, I feel like that's all we need. So we're just gonna do that. And then, whoops, and then we say initializes the game, the new game of live automaton class. And I usually like to put some info on the arguments, double HW, size of CA world, and then device, torch device to use. For now, we won't care about the device, but so the first thing to do is to initialize the superclass with the size and device arguments. Yeah. Oh, and by the way, I think I said that already, but there is no documentation currently for the code base, but most of the classes have extensive doc strings, so that acts as a documentation. But there should be a documentation in the very near future. So maybe when you watch this video, there is already documentation. So what do we need for our cellular automaton? Basically, except from the fact that you need to define a step function and a draw function, everything else is left up to the user, right? I am not asking you to do things in a specific way. All I want you to implement is a step function that will step your cellular automaton by one time step when it's called, and the draw function that will tell me how to translate your world into an image. Okay, and that's all the rest is left up to you. So let's think about it. We want to implement the game of life cellular automaton. So if you're not familiar with it, it's very simple. It's composed of a grid of pixels, essentially, which can be either on or off. And the evolution rules, it goes step by step. each pixels evolve at each step according to the state of its neighbors, right? So the pixel can be on or off, and generally a pixel will turn off if it has less than 2 neighbors or more than 3 neighbors. A pixel will remain on if it has exactly 2 or 3 neighbors. And finally, a pixel will turn on if it has exactly 3 neighbors. So sometimes one way to interpret these pixels is that these pixels are actually alive or dead. And when the population is like too low or too high, the pixels will die. And if the population is just right, the pixel can be burned. So let's think, what do we need to keep track of this world? Well, we just need some sort of matrix that will keep the state of all the pixels. So in this case, we can use a torch tensor. So let me initialize. So we'll need torch. So import torch. By the way, if you're familiar with NumPy, torch is basically the same thing, but allows to use the GPU. So we will make a tensor of size h and w. So you might say, where do self.h and self.w come? Well, these are defined in the automaton class, which should be written somewhere. It's not currently, and this is my bad. But as you can see, they're defined here. Okay. So, and the type of this tensor will be integers because they can be 0 or 1. We could do booleans if we wanted, but then we won't be able to add them. So integers is fine. And do we need anything else? I think we don't, right? This is the state of the world. That's all the variables that we need. So let's go about implementing the step function. So if you look at the automaton, let's go look at the step function. It tells us, please subclass automaton class and define self.step. That's a bit laconic. It should write, this function should update the state of the automaton by 1 time step. Okay. So what do we need to do? So as we said, for each pixel, its next state will depend on the state of its neighbors. We need to count how many on or off neighbors each pixel has. Okay, so right now I'm gonna do the naive implementation where we don't use any parallelization, and then we'll see how to parallelize this, just as an example to see the difference in performance and why is torch useful. But by the way, here to be diligent, I should put device to device. And the device as well is, it is not saved, but it should be. Sorry again about that. That's why there is no doc yet. I promise it's still good. So yeah, let's set the device to self.device. And then let's look at the step function. So we want to compute the neighbors for each pixel. So first of all, num of neighbors of 0. So we want to compute for each pixel. So for each pixel means that I have to go over all the x positions and all the y positions. Okay. And then at this position x, y, we want to compute the number of neighbors. So let me put that here. Then we're going to want to look at all the neighbors. So to do that, we're going to iterate of displacements in x, displacements in y, and let me write sum of, live neighbors is better, okay? And live neighbors, we're going to add to it the state of the world at y plus dy, x plus dx. Okay, so why is it yx and not xy? Because we're using the PyTorch convention where the height of the tensor is the first dimension and then the width is the second dimension. So here if you're sharp, you spotted that we should be careful about the boundaries because we might go outside our tensor. So here we're gonna take a modulo height, and here we're gonna take a modulo width. Okay, and here we are overcounting the 0, 0 neighbor. So we're also counting whether the middle cell is live or not, which in the game of life we should not do. So here we'll say that if dx dy is equal to is different from 0, 0, then we can count the number of neighbors. Add the neighbor, add 1 to live neighbors if neighbor is alive, right? So if self.word is equal to 1, we'll add 1 live neighbor, otherwise not. That's great. And then once we know the number of neighbors, the rules of the game of life tells us what? They tell us that if live neighbors is 2 or 3, and the current cell is alive, then it should remain alive, right? Okay. Else, if we have exactly 3 neighbors and the current cell is dead, then it will be born, survive, and this is birth. So cell.world yx will be equal to 1 as well. And in all other cases, die or remain dead. In all other cases, we don't care what world is, it will be dead. And here I put equal equals when it should be equal. So here, this seems good, but there is a problem. The problem is that as we're going over the loop, we're using self.world to compute the number of neighbors, and we're immediately updating it. So this is a problem. So what we can do is instead like have a new world, which will be the state of the world at the next step, which will be a torch.zeros like self.world. So this means a tensor that is the same as self.world in shape, but that is filled with zeros. And instead here, we will update new world. Here and here will be new world, right? So we're using the current self to compute the number of neighbors and so on. And then new world stars the next state of the world. And so at the end, we can say self.world equal new world. Great. So as you can see this step, each time we call this step, we update self.world to new world by exactly 1 time step by updating each pixel according to the game of life rule. And we're done with step. Now we cannot yet run our automaton because PyCA doesn't know how to display it, right? We just have this world that is values of zeros and ones, but PyCA doesn't know how to turn that into an image, okay? So if we look at the description of draw, it says, this method should be overridden. It should update the self._worldMap tensor, drawing the current state of the CA world on it. So, and they tell us that self.worldMap is a torch tensor of shape 3HW. Again, this is the conventions of PyTorch. And then it tells us, I think, if you choose to use another format, like let's say you don't want to use torch, you're using NumPy, then you should override also the world map property, but this is something else. We don't care because we're using PyTorch. So what we need to do is essentially turn our h.w tensor self.world into a 3hw, so integer self.world into a 3hw float tensor. Okay, so this is again the PyTorch conventions where we have the 3 channels for RGB, the colors, then H, then W. So I will use PyTorch stuff. It doesn't matter if you don't know. You can also do it with for loops. But one way to do that is to say that self.worldMap, so this is the one that we need to set, right? Will be equal to self.world non ... So this is a 1HW tensor. So what I did here is take self.world, add an extra dimension at the beginning here with the none. And so now it's a tensor of shape 1HW. And I will also send it to be a float, right? So self.world was integers, but now I'm turning it into floats because our image tensor, it's floats between 0 and 1. And then I need to expand this to be 3 dimensions, okay? So essentially we have a black and white image for now, and we need a red, green, blue image. So one way to do that is to simply take the current walnut and expand the first dimension. And now it's of shape 3HW. So what this did is just copy the tensor 3 times to have red, green, and blue channels and leave the H and W dimensions alone. And that's it, right? This draw function does exactly what it was asked. It takes our world state and it puts it into world map as a 3HW tensor. Perfect. And as you can see, let's see how many lines of code we wrote. I used a lot of spaces and very spaced code. And in 50 lines of code, we have implemented the game of life. And now it should be able to run in our PyCA window. There is one last thing to do. Into models init, we need to tell PyCA that our model exists by importing it. So from new goal, import new goal. And let me save that as well. So hopefully now if I do UV run simulate, so as before, I just opened the PyCA interface. All right, I'm back. Sorry about that. This was my bad because of the modification of automaton, but everything works now. So as I was saying, if we run our PyCA thing, we arrive and we see this is the same window as before. But if we click here, oh, we see our new automaton. So let's try to see before we crash. It doesn't crash, great. But nothing is happening, I don't see anything. If I press space, things slow to a crawl. It's very laggy, and this is because our implementation is extremely inefficient, but that's fine. While this attempts to close, yeah, this is perfectly normal. It's because of the inefficiency of the implementation, but we'll see how to fix it. So this all worked, but the screen was black. Why? Because of course we initialized the world with zeros. So even if it was running fast, we wouldn't see anything special. So instead, I'm going to put initialize method. So that was great in PyCA. You can make your own methods to add functionality to your automaton. The only ones that you need to define are step and flow. But yeah. And what we'll do is that self.world will be torch.randint like self.world low equals 0, high equal 2. So what does that do? Well, that makes a random integer tensor of the same shape of world with integers between 0 and 2 exclusive, so between 0 and 1. So that's exactly what we want. And here we can just call self.initialize. So now if we run, let's see what happens. New goal is here, and great, we see the whole noise. But let's be careful and not use such a big world. So let's go 50 by 50 for efficiency reason, and let's press space to play, and let's hope that works. Great. So as you can see, the system is evolving. It's not particularly fast. I think it's the game of life. I'm not 100% sure if we made a mistake or not. We can zoom in. So bear in mind that right now, when the FPS is slow, the interface will also be slow. And that's just something from Pygame. There's nothing we can do about it, unfortunately. But yeah, this seems to work perfectly, right? is just slow. So let's close that. And you can stop here if you want. Now you know how to implement a new automaton, but let's still do a small tangent on how to optimize this. So how to implement it using Torch so that it can run in parallel. So it's much more efficient even on CPU. And after that, we'll look into adding interactivity. So the main problem here, as you can see, is this 1, 2, 3, 4 four times nested loop, right? So if we have a world which is like even 10 by 10, this is 100 for the X and Y loop, and then again 8 for this one. So it's at 800 loops per step to do. And this, of course, increases quadratically with the world size. So the idea is to compute this neighbor sum in parallel for all the pixels, right? This makes sense because the neighbor sum of pixel here does not influence the neighbor sum of pixel here. We can compute them all in parallel. So there are many ways to do this in PyTorch. I will do one which is the simplest one. And so what we'll do is that we will create 8 copies of our world, each copy being shifted in a different way. And then that way, when we sum all these copies together as a tensor, each pixel will be the sum of all the neighbors. So let me be more precise. So let's define north, south, east, and west tensors, which will be of self.world, the torch dot, oh, I forgot how this is called, torch.roll. And the input will be self.world, and it will be shifted. So let me remember the shift. Right. So shifts will be, so north, we want to shift by 1, 0. So we want to shift the height, right? We change the height. Then it will be torch.roll, self.world, shifts -1, 0. Torch.roll, self.world, shifts is equal to 0. East, I think it's -1, but it doesn't really matter, right? As long as we're consistent in covering all the shifts. 0, 1. Yeah. So let me, right. So what N, S, E, and W contain is the same world, but just shifted 1 pixel to the right, left, up, and down. Okay. So as you can see, if I do the sum of these 4 tensors, at each position x, y, I will have the sum of the pixels that are north, south, west, and east of each pixel. That's good, but we need also the 4 corners. So let's define northeast, northwest, and then southeast, southwest. These should be the 4 corners that we are missing in our sum. And to do that, we just take the exact same method. So we will shift, we'll shift the north by the amount that gives us east, or -1, torch.roll, north, shifts 0, 1. Then torch.roll, south, shifts 0, -1. These moments is when I miss the AI autocomplete the most. Shifts equal 0, 1. Okay, so this should give us all the directions we need. And now to compute live neighbors, we're going to compute those all at once, right? So live neighbors matrix, let's call it, or tensor to be more PyTorch-like, will be n plus s plus e plus w plus ne plus nw plus se plus sw, right? So live neighbors tensor is a HW tensor for each position contains the sum of neighbors to that position. And now that's great, right? We did everything up to here, and now we still need to do these conditions, right? And again, we would like to ask these conditions all in parallel for all the positions. And unfortunately, we must go through Torch to do that. So, and we don't even need new world because we're going to update world at once, right? So self.world will be torch.where. So torch.where is essentially the if function, but is applied to every location of the tensor, right? So our condition should be a HW condition. So the first condition is this one, right? So torch.where, let me just make this a bit simpler because we're going to use it a bunch of time. Where naive sum is equal to 2 or naive, naive sum is equal to 3. So we cannot use this or. I will say immediately why. And self dot world is equal to 1. So here the problem is that or and and, this is Python stuff. So we need to use the torch bitwise operator, or we also have the option to use torch.or bitwise or. Yes. I think the bitwise operator, I'm going to wing it and say that it's that. And the AND operator is that. If this bugs, I will come back, but I think it's correct. Yeah. If we hover over it, it's the AND that can take 2 tensors, and this doesn't have, but let's hope. So this is again a HW tensor, where at each location contains the answer to whether there are 2 or 3 neighbors and the world is equal to 1. So then, if we look at torch.where, it tells that condition, argument, yeah, condition, input, other. Okay, so it will output input if the condition is true and other if the condition is false. So what we wanted to output if this is true, well, we see here we want 1, okay, and torch will automatically like make this one be a tensor. We don't have to make it a tensor ourselves. And otherwise, we need this to test this other condition. So we need to nest a torch.where naive sum is equal to 2 and self.world is equal to 0. In this case, we want to output 1 again, and otherwise, we want to output 0. And I think I have an extra parenthesis here. That's it. So let's recapitulate. So if torch.where is like if this is true, then we want 1. Otherwise, if this is true, then we also want 1. And in all the cases, we want 0. And we put this into the tensor. And so now we can get rid of all of that. And there you have it. So now let's test this to see if I was correct or not. Let me just make sure that the order of operations is correct here as well. You can never be too sure. Okay, let's run our thing and let's hope for the best. Let's change to new goal, and I will just press play here, and of course it dies out. So let me see. Let me come back once I debug this. Okay, I am back. So my bad, I just forgot how touch.roll works. So we must specify the shifts for each dimensions and then specify which dimension the shifts refer to. So here we're shifting the 0th dimension by 1 and the first dimension by 0. So in principle, we could omit these ones because they're 0 by default, but just to be clear, I added them here. And so now that we have that, if we run the simulation, let's see what happens. So first of all, it's very annoying to always go to new goal when you're developing another thing. So let's change the defaults. So if we go here, interface, then defaults, we can change the default automaton to be, new goal. It's just the name of our class, right? New goal. And now when I run it, it should hopefully start on this new automaton. Okay. Now let's see if I press space. Okay. It is very fast, but as you can see, we have 60 FPS. But this is not the game of life. So let's see where is our bug. So I think the neighbor sum should be okay. So here, if neighbor sum is 2 or 3 and we are alive, then we stay alive. Or here's the bug. Yeah. So if we have exactly 3 neighbors and we are dead, then we are birthed, right? It was 2 neighbors previously, which was not correct. So let's see now. Hopefully we see the game of life. Yes, great. And as you can see, before it basically froze our computer to run the game of life at 250 by 250. And now with this parallelized implementation, it runs super fast. So here, even if I run it with CPU, so let me try. And Windows CPUs are not the best. No, it runs still very fast. Okay, great. So that is the power of parallelization, and that's why it's very important to do it if you want to do any kind of big simulations. Okay, so that's the basic implementation. So now let's see how to add interactivity. Okay, so interactivity. Let's go back to our blueprint, so our automaton, and look at the unimplemented thing. So it's the first 4 methods that are not implemented. So here we have process GUI change. So must be overwritten to respond to GUI component interaction. This we don't care. But here we have process event. Processes a Pygame event if needed, should be overwritten to add interactivity. So that's exactly what we want. Great. So process event, self event. Okay. So the system of events for keybinds and mouse is based on Pygame system. So if you want to know more about how to add different events, you should consult the Pygame documentation, or as is more like of 2026, just ask an LLM. But in this case, as a challenge to myself, I will try to do it without LLMs. But you have all of these cellular automata that have already been implemented, so you can take a look at those to see what you can do. So first of all, we're going to need Pygame. So let me go ahead and import Pygame. And what kind of interactivity will we add? Well, the simplest thing is to add a button to reinitialize the world, because currently, once the world settles, we don't have anything else to do. So let's do that. So here we see we can capture the event that is a key down, and then we can ask if the event.key is a specific key in this way. So for initialize, let's get ki, right? Okay, so this means if the event is somebody pressed a key, and if this key is the I key, then what we'll do? Just called initialize. That should reset the world. And just like that, if I now run my automaton, I can press space, and now it's running. And let's say I want to restart, just press I. And there you have it, interactivity just in 3 lines. You remember that the models had documentation. So here, if you add a doc string to the process event string, I will be re-initialize the automaton, the world. rather. And now if we run, you can see here, automaton keybinds, I reinitialize the world. And that's how you add documentation to your automaton. Okay, what about mouse events? Well, for mouse events, you don't have to bother with Pygame, which is not super easy to use with mouse. You can just use just this function, as you can see here, get mouse state, which if we read the docstring, it says helper function that returns the current mouse state. And then note all 3 mouse buttons will be considered not pressed if control is pressed, blah, blah. We don't care. And we need to pass it the camera. And this is simply because for PyCA to compute the position of the mouse, it needs to know how zoomed the camera is. And then this I will also add it to the docstring, should have already. What is mouse? Okay, mouse is an easy dict that contains some information about the mouse. So typically, we can do if mouse.left. So this is if the left mouse is pressed. Then what we can do is say self.world at mouse.x, mouse.y will be equal to 1. So it means we add, oh, and here I inverted the x and y. Be careful. We will add some matter, and if mouse.right, we will remove some matter. Okay, and let's run this. Okay, so let me go a bit smaller. Okay, let's zoom in. Let's wait for it to settle down a little bit. Okay, and then we can test our mouse. So here I press space to stop the automaton, and now as you can see, I can draw. So, and I can also erase with the other one. So that's it, mouse interactivity. And then I can restart. And of course, our thing also works live. So yeah, so that's for the mouse interactivity. So basically, that's all you need to know about interactivity. The full breadth of interactivity comes really from what you do with it. Okay, so let me show an example of the one which has the most kind of interactions. So if we go to Macelania here, as you can see, you have here K, for example, toggle display kernel. So let me press K. We can see the kernel here. So now I can start the simulation. Down is decrease the temperature. So if I press down, it decreases a parameter, which is the temperature. And as you can see, things are slowing down. And if I press up, I increase the temperature, which is shown here. M can load some new parameters. So really, the interactivity is completely up to you. All you have to do is do it inside this process event and use the Pygame events to detect key presses and the mouse state to detect the mouse. And that's pretty much it. Now for the final thing, which is how to add D elements. Okay, so this is kind of a new feature. So I would say it's even worsely documented than the other things, but I'm working on the doc, I promise. So how do we add graphical user interface? So basically, if you look at the interface here, if you go to PyCA and interface, you have these UI components, which are predefined components that you can use to build your user interface. These are not very clear, but basically you can just use them out of the box and very, very easy to use. So let's see, for example, button. Okay, let's try the button. So from PyCA.interface, import button, right? Then all you have to do is go here and define your button, right? So self initialize button. And as you can see, this is quite informative. So here we just need to get the text that will display, so the text to display on the button. So init, let's say. Then the second is the manager. So it's the pgame UI manager. So for this, all you have to do is pass self.manager. Sorry about that. So let me make a bit more space, which is just the automaton class deals with the manager. So sorry. Okay. Then the parent, we don't need that. Relative position, relative size, none of that is useful. Okay. And even the manager, I mean, you don't really need to do it. It will be done automatically. I think, let's hope. And then all you have to do is to say self.register component and then register the component. Okay. So that tells the automaton that this is a UI component that you added. And then the last thing to do, as we saw before, was Chekhov's gun. In the last thing that we can override in automaton was process GUI change, right? So let's take a look at this function. Must be overwritten to respond to GUI component interactions. This method is called automatically when a component changes its state. To add GUI-based functionality, use this method in your subclass. Great. So let's use this method. And all you have to do is say, if component is self.button, your button, right, that we define. If the component that just changed is the button, where when can the button change? When it's clicked. Okay, so button clicked, right? This is just for and we can do whatever we want here. So we will initialize the state. So now if I run, it doesn't work because, of course, the manager thing was a lie. My bad. You need to include the manager like so. Okay, and here you see automaton controls, we have a button reint. And when we press it, it works, right? So this is really useful. It essentially it complements the keybinds. It's a bit more user-friendly to have these buttons. It's clear what they do when we press them. And you can, of course, add other stuff. So let's make a last change. So let's say that we will change the brightness of our world, right? So let's write. Let's add a parameter, which is brightness, which is equal to 1 by default. And when we draw the map, we will multiply the world map by your brightness parameter. Okay? So for now, nothing's changed because brightness is equal to 1. But we can add a slider for the brightness, for example, right? So what we need to do is from the PyCA interface. So if you go see the interface and go into UI components, you will have, for example, this labeled slider. That sounds good. So let's call this labeled slider. So self.brightness slider. So the minimal value will be 0, or let's say 0.1. Max value will be 1. The manager, whoops, 1 second. Let me turn the light. Actually, it's fine. Manager will be self.manager. And finally, let's say title. Yeah, we want to define the title as brightness. And the tick size can be 0.1, let's say. And the initial value shall be 1, right? Okay, so now we have to register the component. Okay, and finally, we must like do something when the component changes value, right? Self.labeled brightness slider, sorry, it's called, right? When the brightness slider has changed value, what will we do? We'll set our brightness to be equal to the brightness slider value, right? So in the documentation, you will see what each component has as properties that you can access. For now, you need to look into the code, sadly. But yeah, the brightness slider, the slider component just has a value, which is the current value of the slider. So now if we run our simulation, okay, we have here the brightness slider. So I'm still kind of tuning the size of the different texts and so on, but let's see if it works. So as you can see, boom, that's a slider for the brightness. And of course, imagination is the limit, so you can add this component to add some interactivity to your cellular automata. And so this is the end of the tutorial. So this is really an introductory tutorial, which shows you basically the workflow for how to implement your own cellular automaton. But of course, there's much more functionality, which is basically some extra G components and some extra information that you can give from your cellular automaton, like this green string here, which we haven't talked about. But that's basically it. So the richness of PyCA doesn't really come from the framework. The framework is just there to make it simple for you to add this slider and make your simulation interactive. And the real richness is in how you define your automaton class, like what you do in the step function, what you do in the draw function, and all the other functionalities that you add. So I hope you enjoyed this. I hope you enjoyed PyCA, and I'm curious to see what automata you will build. Thank you very much for watching.